Mining involves digging for material or metal deposits found below the Earth's land surface. These deposits are called ores. Ores are essentially rocks, plus unextracted minerals or metals. To explain further, they are solid materials in which these substances are embedded into. Whether these ores come from open deep pits like quarries, or underground in which miners would have to dig deep and create shafts, tunnels, or pipes to reach them, processing these by means of breaking their chunks into smaller pieces provide higher chances for the materials, minerals, or metals to be withdrawn by miners. As we know, metals take up a very important role in the betterment and wellness of anyone's life. They contribute to the structures built in our midst, to the nutritional health background of any individual, and the overall essentials of all the chemical reactions we may fail to recognize around us. Here, you will find out how exactly one particular mineral and metal is extracted from the grounds below us, one so vital that it is actually our body's oxygen carrier through our blood, and is essentially the reason why our blood is red. Here, you will find out the technicalities of iron mining and processing, with a scientific chemical perspective. After excavating iron ores through mining, these have to first be broken down into smaller chunks of material. That way, the iron embedded in them may be extracted more efficiently and effectively. However, crushing iron isn't the only thing one must do in this mining process.
Turning low-grade ore into the most used metal in the world starts at a 200-foot-tall furnace. This is where the iron ore is hit with heat generated by a type of fuel called coke. It's called the blast furnace because as the ore and coke flow downward, they're met by a 1600-degree blast of hot air.
Miners use the very practical technique of smelting. Smelting is when the ores dug up are intensely heated using a blast furnace, which requires a temperature of about 2000 degrees Celsius. The high temperature of the blast furnace allows the iron, or any mineral or metal for that matter, to be obtained more easily, since reducing agents are added in this reaction. This is because a form of impure carbon called coke is added, and thus serves to both heat and reduce the iron ore, based on the reactions it undergoes in the blast furnace itself. A flux, which removes impurities from the ore, may be in the form of limestone, silicon dioxide sand, or dolomite. The coke forms carbon dioxide when it is burnt from the gust of hot air coming from under the blast furnace. This exothermic reaction is thus responsible for how the series of chemical reactions involving heating take place in extracting iron, giving the smelting process. C plus O2 leads to CO2. Now, because carbon dioxide has been formed from heating coke, carbon monoxide is thus formed from heating and reacting with the carbon dioxide from under the furnace. C plus CO2 equals 2CO. This is what serves to reduce the iron ore. Hematite iron ore, or Fe2O3, plus carbon monoxide, which is 3CO, leads to form 2Fe plus CO2, iron and carbon dioxide. Given this chain of chemical reactions from within the blasting furnace toward the iron ore, with heated coke producing carbon dioxide and heated carbon dioxide producing carbon monoxide, finally, iron can be obtained once it has melted enough for it to drip from the iron ore and thus be collected afterwards. First, carbon dioxide is produced by the combination of carbon and oxygen. Carbon dioxide is needed because it reduces ferric oxide. Ferric oxide, which is the iron ore extracted during mining, reacts with carbon dioxide in a redox reaction to produce the impure iron plus carbon dioxide. It is this iron that is finally formed that is purified depending on its purpose as a metal material. 2CO plus O2 leads to 2CO2 plus heat, followed by the reaction of Fe2O3 plus 3CO2 leading to 2Fe plus 3CO2. The rate is dependent on the type of reaction, whether endothermic or exothermic. In the endothermic part of the reaction, during the production of CO2, the rate of the reaction is slower because it takes higher energy for the reaction to proceed. During the reduction of ferric oxide to impure iron, the rate of the reaction is fast because this is an exothermic process and the energy of activation needed is lower, so the reaction easily proceeds to product formation. The habitat of animals, the species of trees, and even the water that is consumed by us human beings are all things that are harmed by the mining of iron. Trees must be cut down in order to make accessible the iron buried underground and under many layers of sediment. Waste flows in the surrounding water bodies, intentionally or unintentionally, or in order to prevent this from happening, dams are built, which also disrupts the local ecosystem. Mining iron harms the habitat of several species of animals, leaving them homeless, destroys different local areas such as forests or wetlands, and increases pollution. The harms, however, aren't restricted only to animals and plants, but to us human beings as well, when heavy metals, which are known to be incredibly harmful to the health, are not properly disposed of, and when the only water source of a community is polluted by a nearby iron mining site. Because iron is so common, it plays a big role in human civilization. Iron, along with steel, accounts for 98% of all ore shipped worldwide. Iron gave even ancient civilizations advantages over their competing nations, because bronze and copper weapons were no match for ironworks. Steel in itself is a form of iron, created with carbon but no oxygen, silicates, or any impurities. This material has proved itself useful throughout human history. Even if you look in your kitchen drawer right now, you will see stainless steel. It's this reaction that allows humanity to avail of these materials. Without this, a lot of the infrastructure would not be the same, and a lot of our common, everyday items will definitely be different.